in this problem, we're going to kind of visualize how the excess molar Gibbs energy affects, the total Gibbs energy of our system. And we're going to do this by essentially plotting our delta G mix. And so in this problem, it's asking us to consider a binary solution of species 1 and 2, so just some two generic species. And it says that these species, their excess molar Gibbs energy, can be described by the one parameter Margulies equation. So once again, it's this A, x1, x2, right? And so what this problem wants us to do is it wants us to calculate and plot delta G mix for three different sort of situations. For cases where our A parameter, which once again describes the strength of the non-ideal interactions between species, where our A parameter is either a value of 1, 2, or 3. Okay? And so in this problem, we want to plot curves of delta G mix for each of these different systems. And then it wants us to sort of describe and interpret what's going on. Okay? All right, and so in this problem, our goal is to just calculate our delta G mix for different A sorts of values in our one parameter Margulies equation. Okay? And so delta G mix, if you remember from chapter 8, we could describe it as just the sum of the delta G of mixing for the case where we have an ideal solution, and then plus our excess molar Gibbs energy term. Okay? Now, if we're dealing with an ideal solution, the delta G of mixing is essentially only affected by the entropy of mixing, right? So RT, and then it's going to be the summation of our xi ln of xi, right? So this is something we derived back in chapter 8. Right, so that's the delta G of mixing. And so essentially what this is saying is, remember, if xi is a value that's 1, or between 0 and 1, and if you have natural log of essentially a fraction, that's going to be negative. And so we see here that due to the entropy of mixing, that's going to make our delta G mixing for an ideal solution negative. Okay? All right, so that's what this term accounts for. And then, for the excess molar Gibbs energy, we're just going to plug in the one parameter Margulies equation, right? And so here, this was saying gx divided by RT. And so here, if we just want gx, we're going to multiply both sides by RT. So we're going to have RT, and then our A, x1, x2. Okay? So this is our delta G mix equation. Okay? Alternatively, we could also plot this as delta G mix divided by RT. And we see that both of our terms here have an RT in front of them. So we're just going to get the entropy of mixing terms, which I'll expand out here. And I'll write them only in terms of the x1 mole fraction. And then the excess molar Gibbs energy. Okay, so once again, this is mix ideal divided by RT, and this is our excess molar Gibbs energy divided by RT. Okay, that's all it is. All right, and so what we're going to do is, in the end, we want this overall delta G of mixing. But to kind of visualize what's going on, I'm first actually going to plot each of these terms individually. So let's plot delta G ID mix and excess molar Gibbs energy separately. And then we'll calculate our delta G of mixing. Okay? All right, so to plot this, we're going to do this in MATLAB. Okay? And so here's an example MATLAB code. And it's a fairly simple code. And so essentially, to start off the code, we just clear out our workspace. And what we're going to do first is define our parameters. So, we want to define a range of mole fractions. So we're going to go from 0 to 1, and we're going to have 1,000 data points in there. We're then going to define another vector that stores our different a values, so 1, 2, and 3. We'll then define anonymous functions to describe our delta G of mixing for the ideal solution, which is this, and then our excess molar Gibbs energy, which will be this. And you can see here that these are the forms that are essentially divided by RT. Okay, so we're actually going to sort of divided by RT so that our functions here are at least directly just functions of the mole fraction. All right, and then also the A parameter as well. Okay, and so once we define our anonymous functions, what we want to do is we want to calculate our G ideal, our G excess, and then the total delta G of mixing. And so for G ideal, it's actually fairly easy because it's not a function of A. It's only going to be a function of X. So what we could do is we could just plug in our X range into there. For the excess molar Gibbs energy and the delta G of mixing, in order to calculate those, we actually need to calculate a for loop because we're going to be changing our A values. All right, and so what we do here is we just define a zeros vector first so that we could plug in our values later. Or it's not a zeros vector, it's a zeros matrix. And so it's going to have 1,000 rows and then 3 different columns. And so each column will be for a different A value. Okay? And then our delta G of mixing is going to be the same thing. And so then we just run a for loop here where we just plug in for the different A values. And then once we have the excess molar Gibbs energy, we just add on to it the ideal delta G of mixing. Okay? And the rest here is just going to be figure generation. Okay? All right, and so we split this problem into 3 different plots. And so for this first plot, once again, this is the delta G of mixing for the ideal case divided by RT. And so once again, this was x1 ln of x1 plus 1 minus x1 ln of 1 minus x1. Okay? All right, and as I said before, these ln terms, they're all going to be negative. All right? And so as we change the mole fraction, we could see that the delta G of ideal mixing forms an upside down parabola, right? And that it's just going to have negative values except when you either have, none of species 1 or only species 1. Okay? And if you remember back when we learned about, Gibbs energy and things like that, for a species to be stable, it wants to decrease its Gibbs energy. And so we see that in this, for the ideal solution case for the delta G of mixing, right, just adding more species in there are going to decrease the Gibbs energy, right? Because now there's going to be more sort of combinations for the system, more permutations when you have the ability to mix different molecules, right? You get to maximize the entropy in the system. And so we see here that the ideal solution delta G of mixing, it's always going to have a negative contribution towards the overall delta G of mixing. Okay? So this is for the ideal solution term. Let's now look at the excess term. And so once again, this excess term accounts for non-ideal interactions. And so we see here that for the excess term, there should be excess, that it has the opposite contribution. In all cases, it's positive, right? And remember, species want to minimize their Gibbs energy. They don't like large amounts of Gibbs energy. And so we see that this excess term actually increases the Gibbs energy in our system, right? We have a sort of upside down parabola. And that, as we increase our A value, as we go from 1 to 3, we increase the sort of magnitude of that upside down parabola, right? And so this excess Gibbs energy, it's always going to have a positive contribution towards the overall delta G of mixing. Okay? All right. And so, we looked at the two terms individually, but now let's look at them when we add them together. Okay? All right. And so, qualitatively, we see that we get three different shapes here. For the case where A is equal to 1, we see that we get still just a parabola. And essentially what this is saying is that the A parameter, even though it's there, the Gibbs excess energy, it's only going to be a minor contribution to the overall Gibbs energy, such that the shape of the curve is just going to look like the ideal solution case, right, where we had a parabola. And so when A is relatively small, the ideal solution case term dominates. Right? When we increase the A value, so we increase the magnitude of interactions between the species, we see that the curve flattens out. And so now instead of having a true parabola, we actually have like a curve with a sort of flat bottom here. Right? And so when A is equal to 2, essentially what we're getting is now the ideal solution term and the excess term have equal contributions to one another. So they sort of cancel out. Right? When we increase A to 3, we now see that the excess term begins to win out. And now our curve, instead of just being a regular parabola, now we have a more complicated shape, where now we have multiple minima, and we also have a maximum in our curve. Okay? All right, and so essentially what we have now is a concave down shape in the curve. And so when we see a delta G curve like this, so I'm going to point out minimum, maximum. And if we go from a minimum to a maximum, that also suggests we have some sort of inflection point here. And also here. Okay. All right, and so when we see a curve like this, where we start to see, minima and maximums and inflection points appear in the curve, what you'll see is that this is actually an indication that we have what's known as a phase separation in our system. So, curve shape indicates phase separation. All right? Okay. And so we'll talk more about exactly what this phase separation means and, how we could actually quantify it. But for now, let me just summarize the sort of things we can interpret from these curves. Okay? And so, for the ideal solution, delta G of mixing, it's always going to have a negative curvature. Okay, so it's just going to be a parabola. Okay? The excess Gibbs energy, at least for the one parameter Margulies equation, where our A values are positive, we saw that they have a positive curvature. That increases as A increases. And then if the excess molar Gibbs energy is large enough, what we see is the appearance of a concave down shape in our overall delta G of mixing. Okay? All right, and so just with this really relatively simple equation, we could gain insight, or we could kind of begin to see how sort of non-idealities in our system will start to affect the sort of stability and what's known as phase behavior of our mixture as well.